Welcome back to the deep dive. Today, we are getting right to it. We're tackling what is arguably the single biggest engineering bottleneck in large audio language models.
The temporal resolution mismatch.
That's the one. Now, if you're listening, you're probably already deep in this space, so you know the pain. You have speech tokens coming in hot at around 25 hertz.
And at the same time, your text tokens, which carry all the semantic weight, they're just trickling in at maybe 3 hertz.
It's a fundamental conflict, and when you try to model them together, that gap forces a really, really tough compromise.
Yeah, you end up forcing the LLM backbone to process a sequence that's, 8 times longer than the actual text content. It's incredibly inefficient.
And since compute cost and attention scales quadratically, even with linear attention, the overhead is huge. You just burn GPU's processing frames that are acoustically rich.
It's semantically sparse.
Exactly.
You're asking the model to obsess over the texture of the sound instead of the meaning.
Which brings us to today's paper. We're dissecting the Fun Audio Chat Technical Report. It's from the Tongyi Fun team at Alibaba Group, dropped it about 2 months ago. And they're proposing a genuinely clever solution.
And they claim to do it without falling into the classic trap of catastrophic forgetting.
Right. That's the other monster under the bed. You teach an LLM to hear, and it forgets how to read.
So their solution has 2 main pillars, both adapted from earlier work. First, something called the Dual Resolution Speech Representations Architecture, or DRSR.
And second, a training strategy they call core cocktail training.
We're going to get into both, and we'll look at their dense 8B model and the bigger MOE 30B A3B scale.
Okay, so let's start with the architecture. The whole goal here was to decouple the speed of semantic processing from the speed of acoustic generation.
Right. They figured, the main LLM backbone doesn't need to hear at 25 hertz. It just needs to understand the flow of the conversation.
So how do they do that? They have this speech token grouping mechanism.
Yep. They start with a standard whisper large V3 encoder, which gives them that 25 hertz token stream. But before that stream hits the LLM, it goes through this grouping operation.
Break that down for us. What's happening at the tensor level?
They take a small window of K equals 5 adjacent speech tokens.
So that's a 200 millisecond chunk of audio.
Exactly. They concatenate those 5 tokens and then pass them through a simple linear layer that projects them down to match the dimension of the LLM backbone.
Okay, so it's a concatenation and projection, not pooling. That's an important distinction.
A crucial one. You're not averaging out the information, you're preserving the features from all 5 frames, but in a single, denser vector.
And the result is the LLM backbone is now operating at a much saner 5 hertz.
Which is much closer to the semantic speed of text. They report this cuts their training GPU hours by nearly 50%.
That is a staggering efficiency gain.
Yeah.
But here's the catch I always see with these compression ideas. The output. If your model reasons at 5 hertz, you can't just generate audio at 5 hertz. It'll sound terrible.
Choppy, robotic. You lose all the prosody.
Yeah. And that's where the dual resolution part comes in. The model have parallel output heads, a standard text head, and then this thing called the speech-refined head, or SRH. So the SRH handles the upsampling, basically.
It handles the ungrouping, but it's smarter than just, simple interpolation.
Yeah.
It takes that final hidden state from the LLM, the 5 hertz representation, projects it, and then splits it back into 5 segments.
Okay, so we're back to 5 slots for tokens.
We are, but it doesn't just spit them all in at once. It can't. Audio is causal. So instead, the SRH runs 5 autoregressive forward passes. It generates each of the 25 hertz tokens one by one using those split segments as context.
I see. So the LM provides the big picture instruction at 5 hertz, the meaning, the general emotional arc, and then the SRH is just it fills in the high-frequency acoustic details.
You got it. It completely decouples the semantic pulse from the acoustic pulse. The backbone can focus on reasoning, and the SRH can focus on making it sound human.
Yeah, it's a really elegant fix, but that's just the architecture. Let's talk training, because this is where things get really interesting with their core cocktail training.
Right, because a great architecture is useless if you destroy your pre-trained weights. In this case, they're starting with Qwen 3 models.
And we all know the problem. Fine-tuning on audio makes the weights drift. Catastrophic forgetting.
So after a basic pre-alignment phase, they move into the core cocktail. It's a 2-stage supervised fine-tuning that uses, of all things, model merging.
Okay, this is the part that really caught my eye. Stage 1, they use a really high learning rate, decaying from 1E4 down to 1E5. That's That's aggressive for a model this size.
It is. The goal is just rapid adaptation. Force the model into this new multimodal space as quickly as possible, but of course that also pushes the weights way off the original text manifold.
So the model learns to listen but forgets how to think.
If you stop there, yes, but they don't. They do this intermediate merging step. They take the stage 1 model, let's call it M1, and the original backbone, M0. Then they interpolate the weights. The formula is Mr. gets alpha times M1 plus 1 minus alpha times M0.
And they set alpha to 0.5.
Yeah.
Just a straight 50-50 split.
It's a very pragmatic way of, pulling the model back. It's like saying, okay, remember all that stuff you knew about language, don't forget it, but you still keep the new audio alignment.
And then stage 2 fine-tunes that merged model.
Exactly. But now with a much, much lower learning rate, from 1E5 down to 1E6, it's all about stable, gentle optimization to find a nice minimum that works for both modalities.
And it's worth pointing out their data source here. They're using high-quality synthesized speech from Cozy Voice 3.
Which is critical. They filter it by word error rate, so the alignment is almost perfect. Using clean synthetic data is a huge advantage when you're doing this kind of careful fine-tuning.
This all seems to point to a bigger trend, moving away from just massive pre-training and towards really sophisticated post-training.
I think that's exactly right. Fun Audio Chat relies heavily on post-training, specifically multitask DPO direct preference optimization.
DPO is pretty standard now, but across 4 different dimensions at once. That seems tricky.
It is, because the objectives can conflict. They're optimizing for robustness, so handling noise, instruction following, style control, audio understanding. And this one, voice empathy.
Voice empathy, that's a tough one to quantify.
And it often fights with instruction following. You tell a model, be concise, and it can kill the empathetic tone. The multitask DPO has to balance those gradients so one doesn't completely take over.
Okay, let's switch gears to the interaction model itself. They have Fun Audio Chat Duplex. This is full duplex, interruptible conversation.
This is the goal for everyone, right? Not a walkie-talkie. It means the model has to process your incoming speech while it's generating its own.
That sounds like an attentional nightmare. How does it learn the logic of when to stop talking or when to let you interrupt?
They synthesize the training data for it. They call the approach omni-flatten. They just generate conversations with tons of overlaps and interruptions, so the model learns to predict end-of-turn and interruption events as if they were just any other token.
So you're baking the social rules of conversation right into the model's objective.
Exactly.
Yeah, let's get to the numbers, the benchmarks. How does the 8B model stack up against others in its weight class, like GLM4 voice?
It does very well. On Open Audio Bench for speech-to-text, Fun Audio Chat 8B gets a 76.61%.
And the competition?
Mini CPM is at 62.58%. GLM4 voice is down at 57.70%. So we're talking a double-digit lead.
That's significant. It suggests that the 5 Hz compression isn't losing information. It might even be helping.
Could be acting like a denoiser, yeah.
Yeah.
And on Voice Bench, which tests robustness, it hits 83.21%. Again, leading the pack.
What about the big 30B mixture of experts model? How does it fare against the closed-source models?
On speech-to-speech tasks, which are the hardest, it's very competitive. On the output-keyboard part of Open Audio Bench, it scores an 88.89%.
And for comparison, what does something like GPT Audio get on that?
GPT Audio is at 83.37% on that specific metric.
Wow. So the open weight model is actually outperforming it there. That's a big deal.
It really is. It shows this MOE approach works well for audio, letting it route tasks to acoustic experts versus semantic experts.
Okay, what about pure audio understanding, the MMAU benchmark?
MMAU covers everything: speech, music, sounds. The 30B model gets 77.9%. What's interesting is the 8B model is right there with it at 76.6%.
That's a really tight grouping. It could mean that understanding ability sort of maxes out around the 8B scale, or that the DRSR architecture is just that efficient for smaller models.
Or that the quality of the training data is the real driver, and it's lifting both models pretty much equally.
Let's talk function calling. This is key for any kind of agentic use.
On SpeechSmart Interact, the 30B model gets 84.13%. For context, Gemini 2.5 Pro is around 79% on similar tasks. So the 5 Hz compression is clearly preserving the logical structure needed for these syntax-heavy instructions.
And the V-style benchmark for acoustic control.
Right. Can it follow speak faster or sound sad? The 8B model scored a 4.20 on Mandarin speed control, which was second only to a specialized commercial model. It shows that speech-refined head has really fine-grained control.
And that duplex model we mentioned, The turn-taking success rate, they report it as 100%.
Yeah, I'm always a little skeptical of a perfect score. It means on their test set, it was perfect. It does blow past competitors like Moshi, which validates their omni-flattened data synthesis approach.
Right.
But the real world is always messier.
To their credit, they are transparent about limitations. The biggest one they cite is context memory,
Yep. In longer conversations, it starts to lose the thread, forgets things you said earlier.
which, it brings you right back to the architecture, doesn't it? The 5 hertz compression is great for efficiency, but maybe it's creating an information bottleneck over longer distances.
That's the trade-off. You smooth out the signal to save compute, but you might also be smoothing out the very details the model needs to remember turn 5 when it's on turn 20.
They also mentioned instability, inexpressiveness, and empathy.
Right, the emotional uncanny valley.
Yeah.
Sometimes it just misses the nuance. It might hear that you're sad, but then respond in a perfectly flat, neutral tone. That's probably those competing DPO objectives we talked about.
But even with those issues, the fact that they've open sourced the 8B model, the training code, everything, that's a huge win for the community.
It's massive. It lets people really dig into the core cocktail logic and the DPO implementation. That's where the real value is for anyone listening to this.
So let's tie this all together. What's the big takeaway from Fun Audio Chat for the whole field?
I think it shows we're moving past the brute force era of just pre-training on ever larger data sets. This paper proves you can get state-of-the-art performance by being smart. You take a great text backbone, you apply an efficient architecture, that 5H 25 hertz split, and you combine it with really surgical post-training.
Shifting the focus from just parameter count to training methodology.
And data quality. It proves that for audio, processing, and generation are 2 different problems that can run at 2 different speeds. Exploiting that asymmetry is how we get these models running on hardware people actually own.
It almost points to a future of, like, edge voice, cloud brain.
That's a great way to put it.
If you can decouple that SRH, the acoustic generation, so cleanly, you could have the high-fidelity 25 hertz part happening locally on your device while the heavy 5 hertz reasoning happens in the cloud.
That's the logical next step for deployment, isn't it? The intelligence is centralized, but the personality, the voice, is rendered right there with you at the edge.
A fascinating place to be heading. We will link the full paper and the GitHub repo in the show notes. I really recommend you dig into that core cocktail implementation.
The DPO loss functions are also really worth a close look.
Definitely. Thank you for joining us for this deep dive. We'll see you next time.